Might not come. Okay, so what did I do last time? We had this X quintic. It degenerated into two funnels. So X1 and X2, or Y1 and Y2. These are funnels. This is a funnel. And this is the quintic Calabi-Yau 3. And this one, this is actually the quartic. This is the quartic. This was the quartic. This was an example. And this was some blow up of P3. So Y1 was the inside P4, was the quartic threefold. Quartic threefold. Y2 was the blow up, some version of P3, but blow up of P3 along some complete intersection curve in P3. And then S was a K3. K3 surface, which is the anti-canonical divisor. Okay, so fine. So we had that. And then we said that via this degeneration, the moduli space of sheaves, let's say in here we looked at sheaves supported on hyperplane sections of quintic. So we had sheaves in quintic, abelian category of quintic, whereas the Chern character was hyperplane section, some curve class, some other characteristic. And this thing degenerated into two relative moduli spaces, My1 over S and My2 over S. These were relative moduli spaces. Relativity was some vanishing of Tor for the sheaves with respect to the divisor S, and that was an open condition in the moduli space. So we said that after all, we need to compactify these things. And we assumed that a nice choice of compactification does exist. Okay? Okay. So we had these things. So a sheaf in here would go to a sheaf F1 and a sheaf F2 in here. And, you know, we needed to have the condition that these two sheaves glue along the divisor in the middle. And, okay, so we knew that each one of these two things can be sent to some sheaf on the divisor, S via literally restriction map. So we're all tensoring with the structure sheaf of S, tensoring with the structure sheaf of S. We call this thing restriction map R2. We call this thing restriction map R1. And then we ended up with this moduli space of sheaves with pure one complex dimensional support on this S. And the picture we had was, we had this degenerate variety over the special fiber, and we had hyperplanes in here and here, like that. And we said, if this relative compactification is possible, then this thing parameterizes sheaves that either do not meet the divisor or non-transversely, or if they do, they meet transversely. And so we had sheaves supported in here and in here, and so via the restriction we get maps from those sheaves to something I can call f of s, which is supported on that curve of intersection. Okay, so this was the, for us, was the moduli space of coherent sheaves with one-dimensional support. One-dimensional support on this divisor S. And stable also. And so, you know, this is actually a known fact that this is the Mukai's moduli space. Mukai's space. And given the Chern characters that I fixed at the beginning of last session, we actually can calculate dimension of this moduli space. So dimension of this M of S is actually smooth of dimension 6. Okay? So, all right. By the Calabi-Yau property, we know that the obstruction theory of this thing is symmetric, so it has virtual dimension equal to 0. And by the fact that Chern character of sheaves in here has Chern character given like this, 0 H1 beta 1 and 1 and 0 H2, these are two hyperplane sections. beta 2, and n2, we can calculate virtual dimension of each one of these, and this would be virtual dimension equal to 3, and this would be virtual dimension also equal to 3. Just the result of Grothendieck-Riemann-Roch calculation. You look at an integral, and you know exactly what these varieties are. This is the quartic, and this is the sum blow up of P3, and you have the Chern character of your sheaves, and the Chern character is given by 2 hyperplane sections, and then curve classes beta 1, beta 2, such that beta 1 plus beta 2 is equal to beta. And okay, you can use Grothendieck-Riemann-Roch to calculate virtual dimensions. The point is, though, that already numerically you can see that you have these 2 relative moduli spaces, and they look like Lagrangians inside the moduli space of the device. Okay? So we also discussed that what we would like to do is, okay, so we know that via these restriction maps, we discussed that we have, if I look at y1 and y2, y1 and y2 relative to s, via the restriction map R1 times R2, I can land on this moduli space. And then here I can embed this thing diagonally in here, diagonally in here, and Junli, so Junli and Wu actually, and in fact, this is Junli's invention anyway, but Junli and Wu actually did it for sheaves as well. So they want us to think that, okay, so we would like for this special fiber of this degenerating family to construct a virtual cycle. So they say that the virtual cycle over the t equal to 0 of this degenerating family, this is what happens at t equal to 0, and this is what happens at t not equal to 0. They want us to define this thing as the Pearson pullback of the virtual cycle of one of them, right, times the virtual cycle of the other. Okay, and this is the virtual cycle on the special fiber. And the idea is that now this virtual cycle on this special fiber actually is going to remain equal to, it needs to prove that these 2 virtual cycles of the generic fiber and the remaining and the special fiber are equal. And when you integrate against these 2 things, integration and definition of invariance on the quintic or the generic fiber of this degenerating family relates to products of relative invariance of y1 and y2. Okay, so this idea was invented by Junli for curves moduli space of stable maps, and then with really hard work and an amazing paper with Wu, they actually extended it to moduli space of not all sheaves, but sheaves that somehow do not become unstable under bubbling. And those sheaves are ideal sheaves, and so this is ideal sheaves, and PT stable pairs. Okay, so these are the things that we knew from the past, but we are doing derived geometry, and I am trying to do something else. We are right now interested in this very fact that we would like to prove that these 2 things are Lagrangians. So this is what we had. And so, okay, so I had a theorem, and now I just start with the theorem. So this was our theorem. So we have a theorem that let Ri these be the restriction maps, M of yi over S to M of S be the restriction maps, okay? The denote restriction maps, which are embedding maps, in fact, then Ri satisfies the conditions of being the condition of inducing a Lagrangian structure. Okay, so that is what it is. So what does that mean? It means that there is some induced map from relative tangent complex of Ri to the cotangent complex of each one of these moduli spaces shifted by -1, which is a quasi-isomorphic quasi-isomorphism of perfect complexes. So in fact, we needed to show that, first of all, Ri's do induce an isotropic structure on each one of these moduli spaces for the closed forms on the moduli spaces, and then we needed to show that the isotropic structure defined by Ri induces a map in the direct category which gives you this quasi-isomorphism. When what was the isotropic structure was that we know that Mukai's moduli space comes with a shifted symplectic structure. It's a symplectic manifold, in fact. It has a two-form, and it's a smooth manifold. And this two-form does induce an isomorphism between cotangent bundle of this manifold and tangent bundle of this manifold, with no shift. In fact, with shift by 0. So this moduli space is a zero-shifted symplectic structure, and it has a closed form, symplectic form. And so isotropic structure means that if I pull back this form back to any of these two relative moduli spaces, first I need to show that the pullback is homotopic to 0, as the same as a Lagrangian does the same thing. If you have some honest Lagrangian submanifold, pullback of the homomorphic symplectic form on that Lagrangian is 0. So we need to show that this, if I pull back this guy back to those guys, I will get homotopy equal to 0. So it lands on a point in the space of all paths from 0 to the pullback of this 2, 4 in the space of closed two forms on each one of these relative moduli spaces. And then I need to show this statement. So first homotopy to 0, let's prove that. So I keep this maybe in the middle so that we have a good view. So we proved that, so to some extent I have put these things in the notes, but I'm repeating them. So we proved that the dual maps, theta Ri dual, defined from L dot of Ri shifted by -1 to T dot of M yi over S are quasi-isomorphisms. And we begin by proving that the isotropicity of the morphism Ri there exists a natural triangle. There exists a natural exact triangle of tangent complexes complexes. For each one of these Ri's, I can see that T dot of Ri goes to T dot of M of Yi over S, and goes to Ri pullback of T dot of M of S. But T dot of M of S, remember, this is a manifold. So this is just nothing but the tangent bundle. It's a swoop, at least in this example. Okay. And now I can translate term by term each one of these things, what they look like. So this corresponds to, which corresponds to RPI lower star of R hum FF times, so I think it is better if I look at my own notes, because I remember that when I was looking at my typed thing, I had some errors. Okay, so this is better. QI upper star of O of XI shifted by minus S. And then, so let me, how should I do it? So maybe I put it in here. So R PI lower star of R hum FF tensor with QI upper star of OXI minus S. This is this term. Of course, it has a shift by 1. Remember that the tangent complex was a shifted R hum. And then this goes to R and PI lower star of R hum FI comma FI shifted by 1. So this is this one. And then this goes to R P I. Let me see.
What is a PI? What is a PI?
I will tell you. RPI lower star of R I. So basically I. How should I? J, for instance, J lower star of LJ upper star of R hum FF. Okay, now I need to tell you what these maps are. Okay. Remember that I'm writing things in the level of moduli spaces. These are moduli spaces of sheaves. So the way you construct, you obtain the tangent complex of these spaces, you look at the universal sheaf. So each one of these moduli spaces, so you have this moduli space on the generic fiber, which is, I called it M. And over here, you have a universal sheaf, and you have the P to M, projection onto M. And then this moduli space degenerates into two relative moduli spaces. Okay? And on each one of these varieties, you have moduli space of Yi, compactified moduli space of relative things on the Yi, okay? And you have projection maps Pi to the moduli space. And so these, with the I, these are universal sheaves on each one of those relative moduli spaces. And so this R hum lives on the whole thing, and then to get something on here, I need to push it forward. And this R hum lives on M times X, but in order to get RP, sorry. Okay. And then, now I need to tell you what this is. Now what this is the pullback of this moduli space. Okay? So there is an injection from S to, so there is a injection from S to each one of these yi. So in fact, I think for these maps, I need to put I and J low, Ji low, upper, Ji lower stuff. So S is being injected inside each one of these varieties, and so it induces an injection.
What is the xi? Xi.
X, what did I have Xi? Where did I? Oh, sorry. Yi. Y. Thank you. So I tell you what it is. So where J, this is where this thing is the natural embedding of S in each of the Fano threefolds. Now we prove isotropicity. Okay, by the way, if you want to know why do I have something, each one of these things, by the way, this also there's a shift by one in here, okay? Everything has a shift by one. If you want to know where is this exact triangle coming from, okay, it's not so hard to see. You just look at the canonical exact sequence. So you have S, okay, and maybe I can put it in here. So you have S sitting inside yi. So each one of these yi, you satisfy an exact, short exact sequence like this. O of S. Okay? So in fact, if you use this, you can take Arham FF, and take Arham FF and multiply, and you will see that this gives you the exact triangle. Okay. Okay. So just so that we know where is the shift. The shift basically sees the normal bundle or conormal bundle of S inside the yi. And so this is what it is, O minus S. And what is this Q? You didn't ask me. Again, Q is the map to the y. Exactly. So for this one, Q is the map to the yi. Qi. In each one of them, it sees the, because I need to pull back that divisor, so that line bundle induced by the divisor. Okay, so in order to see the isotropicity, I actually, now that I know what these things are, okay, so let me write down some exact triangle. So we have the following thing. So for isotropicity, I mean that there exists a path between 0 and pullback of omega, and this is the omega of ns in the space of closed two forms on each one of these compactified relative moduli spaces of degree n. Okay, so how do we see that? So look at this exact triangle. So what I'm going to do is, I know this is the case, okay? So what does this thing do? This thing, I can put this tangent bundle over there, or I can put this over here. This is a this is an isomorphism. I can think of it as a map from tangent to omega. And then I can dualize omega. And I can see that omega, this omega, I can see that the symplectic form is realized by morphism in the derived category from T times T to O. So all I need to do is I pull back this morphism from this. If I put this in here, it becomes t times t. All I need to do is to pull back this morphism from t squared to O back to the MYIS and show that that complex I get is quasi-isomorphic to 0. That's what I should show. So let me show that. So we have this, we get after pulling back, we get this exact triangle, this commutative diagram. So we have the form on each one of so we know that there is a form in here, actually y1, yi actually, again yi, like that. On each one of the relative moduli spaces, there is a form from here to here. Okay. Okay, and so then, I think, yeah, so that's good. Okay. Yeah, that's totally fine. Okay. Remember that these are Fano varieties. We had this statement that if you have the moduli space of perfect complexes, it's always coming from a two-shifted symplectic structure. If you have the moduli space of perfect complexes on a variety of dimension d, it always comes with 2 minus d shifted symplectic structure. So already you have the shifted symplectic structures. So okay, so and then you can get a map by just pulling back using the exact triangle. Because each one of these yi's communicates with the pullback of this thing. So it gets mapped to Ri upper star of R high of S lower star, R high, F of S, with a tilde on it, and shifted by 1. Times itself 2 Ri upper star of O and S. So this, in fact, is the symplectic form on the M of S. This is symplectic form on M of S. So it's a map from tangent to tangent to O. Okay? Right, so you have that thing. Okay? Now, this naturally, where is this map? Where are these maps coming from? I think it is obvious where they are coming from. So there's M of S, and then there is a map from R I to M of yi over S. These are the restriction maps. You take cotangent complex of M of S, so you take L dot of M of S, for instance, pull it back, Ri upper star, you get the map from that L dot of Mi over S to L dot of Ri. You can also dualize, which gives you the map from pullback of T dot to T dot of those, and then to T out. Are we? The maps should be backwards, right? You agree? Maps are not correct. Why did I put it like this? Yeah, it should be backwards. map from T dot of Ri to T dot of M. Oh no, it's correct actually. And then to R upper R star of T dot of pullback of T of M of S. Oh, it was correct. This is that thing. So this is this way, and then this is this way. So this is R upper star of T dot of M of S times Ri upper star of T dot of M of S. Each one of these factors gets mapped to here. So that's it.
Sorry, can you explain the upper line map?
Yeah, upper line map is the choice of symplectic structure you get there.
But syntactic structure go to all M. Why do you write go to?
No, but it goes to all of them, but this is also all of them.
Okay.
It's the push forward. It's on M. The reason I get this map is because the way I get this commutative diagram is because I translate these terms. I know this is an Arham Fi Fi, this is an Arham Fi Fi. I know what this is, okay? And you have that exact triangle, that which I wrote. Over here, I wrote this gigantic exact triangle. Then naturally, we get if you just follow that exact triangle, you see that this gets mapped to here, and that gets mapped to here, and then it gets mapped to here. Okay. But then, actually, but if I have, so anyways, so I think this should be okay. But again, as I told you, this is something that I did myself, so it might have some errors, but I don't think there is any error in here. However, note that R2 Pi over star of O of Yi tensor with M of Yi over S is equal to 0. This is the cool part. You get this commutative diagram, and you actually see that this thing, the symplectic form that you, after pullback you get, gets mapped to 0. Why is this? Because if you look at fiber-wise, if I have a point P in any of these moduli spaces, and I look at the fiber of this guy over that point P, it actually gives me cohomology of Yi. This is just cohomology of O. So this basically just gives me xi of O yi O, or xi or hi yi O, chief cohomology of these things. And this fiber-wise calculation is enough because you can actually see that by Kodaira vanishing, this guy vanishes. So this is equal to 0 by fiber-wise calculation. And indeed, Kodaira vanishing. Why is it by Kodaira vanishing? I mean, you have this, these guys are funnel. These guys, Yi's are funnel. And basically, all of these HI's less than the dimension of the variety, all of them vanish for funnel. Because the funnel, because the canonical bundle of the funnel is anti-ample, and you can actually see that these all vanish.
Okay. So for that map, you mean
For I less than 3, these are equal to 0.
I was wondering for the upper line map. You mean it's a map to all of M, but it's factored through.
Yes, that's right. That's right. That comes from the construction. Yes. Yes. Okay, so this gets mapped to 0, and so which means there is a homotopy map between Ri upper star of omega of n of s and 0. Okay, so it might be that my proof is a little bit sloppy, which I agree, because it's really just my proof. But roughly, I think this must be correct. But I could make it better, but I didn't have time. Yeah, so that's, I think, I don't need this commutative diagram anymore. So I have now proved that these RIs are isotropic structures. They give me a map, a path from 0 to the pullback. So the first condition is now satisfied. Now we prove, by the way, I heard from experts that this kind of thing probably has been proved somewhere else. And maybe it is somehow camouflaged in the work of Damien Kalek. I kind of didn't find it precisely the way I put it in, because I'm applying it to degeneration, and for me it's just a little homework thing that I thought, is this correct? I mean, can we use this? And it seems like it is working, but maybe, yeah. So it is not something very surprising for the experts in the community. I think what could be interesting for the experts in the community is that whether you show, I mean, I think overall the community believes that these are Lagrangians. Okay, I'm explicitly actually trying to prove it. Probably it's even proven, I don't know. But what is interesting is that now that if you prove that these are Lagrangians, can you use Lagrangian intersections to calculate invariance? So any computation using this derived geometry business and using the property of these being Lagrangians is interesting. In fact, I'm saying it even better. If we prove that these are Lagrangians, then we know that their fiber product over these two maps, over here, is going to be a -1 shifted symplectic structure by the theorems we had before. And so by the local Darboux theorem of Joyce, the fiber product can be written as a critical modulus of a function, Chern-Simons type function. So calculate your invariance using Milnor fiber and the vanishing cycles of that function, that potential that you compute. Maybe we are actually able. I'm actually doing an example of this thing myself. Some very, 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 very simple example. Sheaves on the hyperplane section of Coitic and degeneration, but the sheaf I don't want to be complicated at all. Like a sheaf is, let's say, it could be ideal sheaf of a point on that hyperplane section. It's modulized this over the thing. It's just a hyperplane, but then there's a linear system of those hyperplanes. Okay, so work it out. So you have this linear system, it degenerates. See if you can calculate this potential. See if you can calculate the Milnor number. See if you can calculate the result of Julie's thing. Then it's valid. But I think what I'm telling you in here is interesting for me particularly, but I don't think it is something that people don't know. This I asked people. I mean, Dennis told you. I mean, probably many people know this. Okay. Okay. So now we proved that this isotropic structure induces a. Now we proved that this isotropic structure on Ri is a Lagrangian structure. consider the following exact triangle. Induced by exact triangle induced by degeneration of x to y1 union y2 glued along S. So what is that? This is the T dot of M of x now goes to Ri, R1, R1. Now I'm seeing both of them. R1 upper star of T dot of M of Y1 over S plus R2 upper star of T dot of M of Y2 over S and I upper star of T dot of M of S. So in the total space of this degenerating family of modular spaces, okay, I can pull back everything there. These are all divisors. First, think about varieties. You have X degenerating into Y1, Y2S. And then okay, so X has a tangent bundle. And each one of these have tangent bundles. Okay, and this one too. So you can map, this degenerating family, in fact, gets mapped to S. You just need to, project onto the special fiber and then project onto S. So you can pull back tangent bundle of S. You can pull back tangent bundle of each one of these. And they satisfy exact triangle. And we are writing this thing analog of this thing, but in the level of the modular spaces. Okay, there's a whole family of modular spaces. Fiber-wise, it's given by the modular space of sheaves on X. Okay, and then over the special fiber, you have something else. Okay, so you have that, and now you apply Serre duality. Now I am going to delete this, and I'm going to put it over there. So you now apply Serre duality along fibers, and to each term in the triangle above, and obtain the following commutative diagram in derived category. So what do you get? You will get that, so this is something I'm not going to erase. So you have, so you will have T dot of M of X goes to, I'm writing that thing down, T dot of R1 upper star of T dot of M1 plus R2 upper star of T dot of MY2, okay, and then you go to pi upper star of T dot of M of X. And then if you apply, each one of these things, remember that these are tangent complexes. So these are shifted by one R harms. So if I apply Serre duality, I will basically get these maps. So this is quasi-isomorphic via Serre duality to R P lower star, not Pi, but just P, R hum, FF. It's a Calabi-Yau. The Serre duality just gives me a twisting by O again. And then shifted by -1. Serre duality. And then this is a 2. So then this becomes sum I1 to 2 Ri upper star of R Pi lower star R hum Fi, all the universal sheaves, times Qi upper star of the canonical of Yi's. Again, Serre duality. These are R hum Fi shifted by 1. When I apply Serre duality, I get this tensoring with the canonical bundle on each one of them. Good. Then I need to put a dual in here, and the shift by 1 becomes a -1 shift. So this is okay. Okay? And then the last term is just the high upper star of R high lower star of R hum F of S again shifted by -1 and with the dual. Okay. So that's it. We're all vertical maps. Vertical maps are isums in TB, draft category of the whole matrices. Okay, now note that. Now here is the cool fact. I can focus on this one, and I can see something nice happens in here, which is this sum I1 to 2 Ri upper star of Rp I lower star R hum Fi, this thing, times the Qi upper star of K Yi, this thing with the shift is isomorphic to, in fact, R. Okay, so this is R1 upper star of RP1 lower star of R hum F1 tensor with the Q1 upper star of OY1 minus S. Remember, S was the anti-canonical divisor, right? So the canonical is that, Y1. Okay. Shifted dual, shifted by -1. Okay, plus, this is for 1, plus, why is it that I'm expanding this thing? Here's the complication that happens when you think that everything is going smoothly, but then you realize that one of your varieties is literally just a quartic, but the other variety, because we wanted to make the total space of this degeneration smooth, we blew up that variety. So this thing, this is the K3, and this one is the blow up of P3 along some curve. So I cannot just take the canonical bundle of P3, which is O of -4, the quartic. I cannot do that and put it back up unless I add the exceptional divisor of this blow up there. took the total space of this family. Before this, it was like this, and I blew up along this P3 as a weight divisor, which had a locus of singularities. So, so this I will get something like R2, but I modify it. So I exactly know what is the canonical bundle of that thing now. It's the canonical bundle of P3 plus the exceptional divisor. So I will just need to modify it, which is okay. I mean, it's not much of the trouble, but I'm just trying to be careful in here because Q to upper star over Y2 minus S plus E shifted by minus 1. Okay? E is the exceptional divisor of blow up of P3 along that complete intersection. Okay, so this we get. Alright, so what I need to put in is basically I need to put in this thing in the middle in here. Okay? It's not really bad actually. So, this is what we get. Now, via this third duality, we realize that this thing on the nose is just L dot of R2. On the nose. The L dot of, R1. And plus this other term. This other term is not exactly L dot of R2. Remember that I put in a description for the T dot of R1 and R2. Do you remember that? I did put that thing. And I told you that these see the twisting by minus S. If you look at that description, you see that this is actually L dot of R2, okay? Earlier in your notes. Now, this is also almost the L dot of R2, but except because I blew up this thing somewhere, it's different than L dot of R2 by a twist, by this E. So in fact, you can get a map from L dot of R2 to it. So there is a map from L dot of R2 shifted by minus 1 to this guy. So this is honest to God L dot of R1, right? And this is not honest to God L dot of R1, but it is L dot of R2. But it is, but there's a map from here. Okay then. So then that actually tells me, okay, so let's stare at this for a while. So I hope it is obvious. So I'm just using duality and I'm retranslating what these things are. For this one, I put O of minus S. For the P3 part, I modified it. And then I realized that this is L dot of R1. And I realized this maps to that. So I'm almost done actually. So now via this, I can actually see that I can complete this diagram. So you can see that there is L dot of R1. Oh, sorry, L dot of R1 shifted by minus 1. I'm sorry. Both of them have a shift by minus 1. So via this identification, you can actually see that this guy plus this guy, L dot of R2 shifted by minus 1, this does get mapped to here, to this direct sum. I have expanded this thing down here. So this piece plus this piece get mapped to here. And so in fact, naturally there is a map that factors through here, and naturally there is a map that goes from here. Okay. So, okay. So you can also, these are quasi-isomorphisms, so you can look at this one. These are quasi-isomorphisms. Same. So voila, you almost have it, right? So look at it. I am looking at this term in here, and I'm going above that. Only that I need to tell you something that what it does twisting by this e. So note that e is the exceptional divisor of the blow-up of P3 along this curve, exceptional divisor, and so we get the diagram as I have written here, okay, where the upward arrows between first and second rows, are the inverses of the vertical maps, vertical isomorphisms that we had before, that we obtained by Serre duality. And furthermore, and so I can now delete this lower bottom. Okay. Furthermore, you can see that the quasi-isoms given by first and third vertical maps, first and third vertical arrows, and the fact that homomorphism from O of y2 to O of y2 twisted by E is isomorphic to C, imply that the composite morphism in the middle vertical arrow is a quasi-isomorphism. So basically, I'm looking at this thing in here, I know that this part of it is just isomorphic to R1 upper star, but this part just gets mapped. But you can work it out, and you can actually see that all you need for this composite map to be quasi-isomorphism is that this statement holds true, but this statement doesn't hold true. This is the exceptional divisor. This is just C. Okay? And so you will get eventually that the final result that, so you see that R1 upper star, L dot of L M, Ri upper star, L dot of MIS, I from 1 to 2, to the Ri upper star of T dot of MOS is a quasi-isomorphism, which is basically what we wanted. These are split. And so this is essentially what we wanted to actually prove, and this finishes the proof. Okay, so these are quasi-isomorphic, so as a result, in fact, corollary of this result is that immediately you realize M1 over S fiber product with My2 over S over M of S has a -1 shifted symplectic structure. Okay, and for the whole fiber product, that's virtual dimension 0. The whole thing is virtual dimension 6. 3 plus 3 minus 6. So the virtual dimension 0. It's like the modular space of sheaves over a Calabi-Yau thing. It's a singular Calabi-Yau, of course. And it has -1 shifted symplectic structure and can be written as a critical locus. And by Joyce et al. Local Darboux theorem can be written as critical of some degree 0 function on the underlying DG algebra of the derived fiber product of these two things. Okay. So, by the way, I said that this is known to the experts. There is a lot of interesting things about fiber products, and this is where Damien Kalak has worked on these things. So I think these are trivial to him, most probably. He never applied it to degeneration, but I think he knows it, or maybe it is there. So, anyways, so this is what it is, and now it is interesting if you can actually. If someone is interested, I have plenty of projects on this. We know the degeneration, we know exactly what it is. In simple examples, I can come up with the compactifications because I explicitly know what's the moduli space of sheaves relative to a divisor. For instance, if you pick a hyperplane section of quintic, you're looking at moduli space of ideal sheaf of a point on that hyperplane section. Relativity condition means over the degenerating family, the hyperplane breaks into two pieces, and you would like to make sure that this point does not fall inside the divisor. So you can bubble up a couple of times, in fact only once, and it would not fall inside the divisor. So you precisely, in fact, know what's the moduli space. You exactly know what this is, and you exactly know what this is. Okay, and you know that this result is correct. Calculate this space. I think you can. There is a potential, and you can calculate the window now. And I think it will get matching. It will get that invariant of the moduli space of the generic fiber matches with the invariant of the singular fiber. More interestingly, a project I could define is look at the moduli space of coherent sheets on toric column. For instance, local P2, good example. In fact, invariants of this moduli space have been calculated using motific computations for all possible sheets, in fact. Yoon Shi she's an academic sister of mine, student of Sheldon Katz. I think she has calculated this for local P2. And she has choice of an orientation data that we had in here, so her calculation depends on the orientation data. She shows that there is an orientation data. She shows that her moduli space is written as a critical locus. She calculates motifically the numbers using the motive of the vanishing cycles over the generic fiber. Okay, calculate the same thing over the spatial fiber and show that they are matching. Now that we have all of this. So there are plenty of things in enumerative geometry that one can do. On toric varieties, often these moduli spaces of sheets have quiver description. We can actually show that there's a quiver description. We can actually show that on that moduli space of quiver representations, there's a potential, and you can calculate.
What is the name of the invention?
Name of my sister.
You just mentioned it.
Yes, Yoon Shi. Yeah, I think. She calculates these moduli space of coherent sheets, invariants of the moduli space of coherent sheets on local P2, for instance, using motific. She calculates motific DT invariant. So okay, and then quiver representations. I mean, this potential and quiver representation. There are many people. Ed Sigal. He showed that for local P2, it actually tells you what's the quiver representation of the moduli space of coherent sheets, and he shows that there's a potential there. So there are plenty of things. There are many names I can put in here. There is this. There is Ored Ben Basat, who in fact, whose name is one of the. We mentioned him a lot. BBBJ. I mean those papers of Joyce Ben Basat. These are all names that come to mind. All papers of Joyce, of course. There is a good friend of mine who also calculates things motifically. There is Ben Davison, whose papers I think could be interesting. These are all motific calculations. And of course, Kai Barrett. Anything that Kai Barron wrote on these motific things, anything that Balaj Sandrui actually wrote, he's in fact the expert. I mean, I should put a circle around him. So he's the one who somehow has created this topic. Anyway, so this is an example. I think I convinced you that it's useful. The derived geometry is useful. And yes, often people ask, can we calculate numbers? Yes, we can calculate numbers. That is my point. If you really dig in and you zoom into these definitions, you can actually calculate this. This you can calculate. Okay, so this is, I stopped today here. Next time, we will do, there is some nice paper of Calderaro and Arinke. It gives insight about, again, the derived intersection product. And what kind of things we can do with it. So I do that next time. But I think this is a good place to stop on the relations between derived geometry and the moduli space of sheaves. I wanted to discuss moduli space of coherent sheaves on fourfolds. The reason I didn't do it, I looked at this paper of Dennis was here, Dennis, Borisov, and Joyce, and I realized that takes another 10 sessions. They did local calculation, and it's horrifying. Yes, that thing is horrifying actually. And plus, that's a local thing, and with Dennis we are actually obtaining the global description of the moduli space. Global construction of this function that gives the moduli space as a critical locus. So it would maybe it can be written soon, and you will see it. But that's why I didn't do the fourfold. All that you need to know about fourfold is that its moduli space of coherent sheaves is -2 shifted symplectic. It is written as a critical locus, but this time the function doesn't sit in the degree 0 part of the underlying DG algebra of the moduli space. It sits in degree some other degree 2. It's a degree 2 graded potential. So on the underlying algebra of the moduli space, this function sits in A2. And you can actually, in some examples, you can show that it's easy examples. Okay, so let us